Right. Yeah. So let's begin. Who's heard of transformers before? Raise your hand. Oh, about half. Okay, half. Attention. Who's heard of attention before? Great. About half. Great. Well, so today's lecture, we're going to dive into what the attention mechanism is, and then see how folks have used this sort of building block to build architecture that are known as transformers. And then we're going to see how transformers have been applied to a variety of tasks. So we're going to motivate most of this from NLP and machine translation, these type of tasks. But by the end of it, we're going to see how transformers are now starting to touch a wide variety of typical tasks, ranging from computer vision to all the way to protein folding. This is the last in our series of kind of explaining various kinds of variations of neural architectures, and it's going to link quite closely with what Ferenc was telling us on Tuesday. I've designed this lecture, let me see, is it advancing? Yeah, designed this lecture very similar to last Thursday. You might cast your mind back and recall last Thursday we talked about convolutions. And so I designed that lecture primarily to talk about the convolution operator. And then once I explained how that worked, we then looked at how it's used in architectures and all the other variations that go along with it. And so very similar today, we're going to focus a lot on this attention mechanism. And once we've understood what it is, what can it buy us in terms of model capacity, we're going to see how it's incorporated at scale into architectures known as transformers. At the end, if there's time, I'm completely happy if we spend, like, let's say 70% of our time on these first two items. That's completely fine, because those are the main things I want to get across today. But as time permits, we're going to look at the last 2 points here that look at extensions on transformers. So there are some scalability issues, for example, that seem to be the focus of what a lot of the innovation lately has been about with respect to transformers. And then finally, I want to make sure that we understand that they're much more generally applicable to other applications beyond NLP, to things like image and so on. And excitingly, I'm able to announce next Thursday, we're going to hear about transformers being applied to NLP and other, to images and so on from a guest lecture. So we're going to dive into other forms of transformers. That's exciting stuff. So let's motivate and start to introduce this notion of transformers by a design that we saw on Tuesday. So the end of Ferenc's lecture about sequence-to-sequence models and recurrent networks and so on, we started to see networks that look something like this, right? Where we had an encoder architecture at the top that you see here, and at the bottom we have a decoder, and in between, what joins them together is what is known as a context vector. And he was describing how people use this context vector and describe what it's able to sort of encode as thought vectors or other types of terminology, which really are just talking about how you can distill the information that's extracted from this input sequence into a sort of a vector that is then digested at the decoding stage to produce an output. And in this example here is one of machine translation. And so the way it works is that you can imagine this context vector being filled as it starts to digest this English sentence. It goes from she to is to eat, a green apple. It's going to encode the necessary information that the decoding architecture is then going to utilize to produce a Chinese output. Now, the motivation for attention comes from the fact that there's a few limiting factors in this design of context vectors. Does anyone want to suggest a limiting bottleneck in this type of neural architecture design? I've got 4 chocolates here today, so we can go through all of them. What would be a limiting factor in this approach? Yeah.
The vector is length 5, so in order to about 5 things.
Oh, I'm sorry, I couldn't quite hear.
Vector's length is 5, which limits us to store on 5 things at the same time.
Exactly, that's a good one. Yeah, so exactly. So we have a fixed length vector, and then but we're trying to design and train a general purpose piece of machinery that, where the objective here is to translate language. And so you can imagine that this piece of this model, it could be trained, it could be used on any type of sentence. It could be provided a very complex sentence, so maybe a bit of poetry or something that has a lot going on, is very deep, has all these different layers of meaning. And yet we have this very limited fixed context vector that we're going to also try to decode the most basic sort of information, maybe just a tweet or a very sort of straightforward piece of information, right? A very short sentence. So the fact that it's fixed is one issue. The other issue is that Oh yes, it does. The other issue is that it's only able to learn one type of mapping. So obviously, as I mentioned before, the complex sentence can have lots of different types of semantics necessary for a translation to occur. So one thing you might, an example we're going to use a few times in this series of slides is that often when you're doing translation for easy words, there's like a one-to-one correspondence. So that's one type of mapping you want to encode in this vector. But there's other types of information too, like other languages that might have different order of words, and you might need to look at a sort of a different combination of words to really discern what that next word really should be. We'll see an example of that coming on. And it's very difficult to encode all of these different types of mappings and relationships that might exist within a single context vector that's going to be continuously used. The mapping function that generates this thing is fixed. So it's going to be always used regardless of the input. So that was a limiting factor. And so I'm going to use that as a motivation. And so I know that we have a lot of the tendency to just have a lot of slides and talking about slides. So I thought it might be interesting if I try to draw something. And I was sort of doodling in my office trying to think of an illustration to kind of get at the heart of the idea that I want you to sort of take away. And so if let me see if I can get this drawing thing working. Drawing, yeah, looking good. Okay, so what I've just described is, let's call this old. It was the old way of using context vectors that had this bottleneck that limited us, for example, when we started to use it in more complex tasks. And the bottleneck was that we had this encoding. This is a illustration of what we just saw. So we have this guy here, data coming in, and then we learned this fixed mapping function that could generate a context that was always going to be the same number of same lengths regardless of the complexity of the input, that we could then use to generate the output. With a motivating example here is translation, but it could be, for example, the text synthesis stuff that our friends showed us last time. So what's the new innovation? Let's call this new. Well, folks looked at this problem and they wanted more expressiveness in the context vector. They said to themselves, well, I don't want a fixed mapping that's always going to be there regardless of what type of input's coming in. I also want to have the ability that as I have larger inputs, I can build larger context vectors and use those to do the decoding part. And so that's what they motivated them. And so like anyone else, they started to think, what mechanisms could I dream up to provide this facility? And so let me just draw another input layer here, input encoder. To generate this context vector, they're going to learn what you can imagine is a weight that parameterizes a function to generate this context vector, right? So the big idea in this new paradigm is that we're not going to learn weights anymore that produce a fixed context vector. Instead, we're going to learn a function, and that function is going to learn weights. And then we're going to then use those weights to generate the context. And we're not going to do that only once. We're going to do this continuously as we pull out new output. And so let me explain exactly what that means. But the heart of the innovation here is that on the left-hand side in the existing paradigm before attention, we just learned these weights. Now we're going to learn, I'm calling this a function that's going to generate weights. And then we're going to use these weights to generate context vectors multiple times. So then let's see, let's draw the output here. So then what happens is, as I start to do, for example, this machine translation task, for example, if I get to this first element here, I'm going to not just access this fixed context vector that's going to be the same for each of the elements. I'm going to use this function to, so I use this function to generate a context vector, and then use this context vector to generate this output, right? So this context vector might be perfect for doing one of these one-to-one mappings. I have one language, I have a word for cat, and then another language, I have another word for cat. Whatever that's gatto in Italian, right? So it's a nice one-to-one mapping, and then this context vector is perfect for that use case. Then when I get to the next element, because I'm no longer restricted to the same context vector, I can call this function that's that the inputs to this. Oh, what's happened here? Let me yeah, this will do. Where the input of this function here is this whole encoding, I can call this function again to produce this next token here. And what it's going to do is produce another context vector. that's based on these weights, but because I call the function again, that's going to be parameterized by both the input and the prior context, it can be a brand new set of relationships. And so then I can slowly build up larger and larger context vectors based on the, based on the input. And then those relationships the context vectors encode can be unique to the task at hand. Because it's not a fixed mapping, it's a mapping that's produced by a function that's parameterized by the input and the prior context. And so this is the new facility that we're going to have, that we're going to call attention. The reason why it's called attention is that as it builds up these contexts, they're going to attend to different parts of the input with different strengths based on what relationship they're trying to exploit. So the first type of translation I've been talking about, this one-to-one mapping, and I don't know anything about translation, to be honest, but I think that's the way I think of it, at least. It might heavily attend and be built from this first token of the input, because perhaps those two words align very well in the input and the output. But then for these more complicated relationships that we're going to see later with prettier slides than this, the relationship we're talking about might attend to maybe 3 or 4 words later in the sentence that provide really important information for understanding what the appropriate translation of this word is as we populate this output. So that's kind of the key idea. So you put that in your pocket and walk out of here, I'm a happy guy. Let's unpack this further so we can understand really what I'm going on about. I'm going to stop drawing and clear this and progress. Okay. Yeah, cool. So the next question is, once you've had this idea about this ability to learn a function and have this be the generator of the context vectors rather than this fixed mapping, the question is, how are you going to use it? And so the first time that people started to use this facility was in this 2015 paper, where the way I'm always confused by when people start to change these type of drawings. I never quite can understand things until someone explains it to me. So I'll explain that the diagram here I want you to understand is on the right-hand side. All we've done is flipped it. So now the inputs at the bottom. So x1 through xt is the inputs. We've unpacked this nice encoder to show a few of the hidden states. So that's what's been going on here with the hidden states, H1 and so on, bidirectional. And then it's flipped, right? So the generation, the output is happening at the top here. So now we're on the same page about how to read this diagram. Let me explain how we're generating these contexts in this first use of attention. And so we have, if I move forward one slide. Yeah, okay. So as I mentioned, at each time we generate another output, we're going to generate a brand new context vector that's appropriate for the type of generation we're going to do. And so this is what this figure is illustrating here. You can think of this symbol here as being the context that's being generated. And then the idea of, in this particular form of attention, there are 2 main things happening. So I talked about how you're going to attend or focus on different parts of the input encoding, right? So what the design of this generation function has 2 main equations that we see shown down here. If you see my cursor, the first equation here is simply just doing a normalization because we want to weight. So any numbers that we generate, we want to have those numbers sum to 1. So they're a weighting. And then the function below it is what is input into this normalization function above. And what this function below does is uses a fully connected network to decide what these weights should be. And it needs to be normalized because the output of that function or fully connected network could be any sort of value, right? So we need to normalize it so it's this nice property of 0 to 1, so it's a weight. And then if you look at what it's using, I've illustrated it here on the right-hand side. It's using both the prior state. So remember, these are you can think of these as tokens being generated. This is like we're doing a translation task, and this is the word before it, and this is the next word. So when it generates this context, it's going to be conditioned on the prior word, as well as the hidden state of not only the first word in the encoding, but all other words, because we see that to generate this context here, it's going to be comprised of a series of weights that are shown here as alphas. And so what's being illustrated here is the very first alpha that's saying, what is the weight of the first item in the encoding going to be for this particular context vector? And then as you go through, it's going to use it's going to calculate what's the weighting for the next alpha, again, because we've just got a function here that tells us how to do this. And so we can go through all the different alphas that are, alpha is a weight for a particular part of the encoding. And then we use all of these to produce a context vector that is going to apply for just how we're going to produce this next token. And so that is how the very first realization of this idea of a more dynamic and higher capacity form of context vector came about. And as we go through these slides, you'll see the idea evolves. But what was very exciting was when folks started to use this mechanism, they got really exciting types of behavior. And so this is a figure that you would have seen in Ferencz's slides on Tuesday. But I think now with a bit more ammunition to understand what's going on, we can highlight some other types of outcomes of what's being shown here. So what you're seeing here is a translation task from French to English. So we have the we have the French on this dimension, English on the Y dimension, and then these colors. These colors are all the alphas, right? So in the case where we're going to produce a translation, we're about to generate and say, okay, what word should come next? And when I'm trying to translate this whole sentence that I've had in my encoding here, as I'm generating and as I'm decoding the translation, what are the appropriate pieces of input for me to use when I generate the next word that happens to be economic? Well, then these colors here are a representation of all the alphas. And so for a word like economic, you can see that it's really heavily going to consider this French word économique or something. And so this is the mechanism that's described at work. And so they're able to see that not only can it learn the right relationships, so this is what we're seeing here. These are also, you notice that the alphas that it's parameterizing for other words in the sentence are not being listened to at all. It's irrelevant when you're trying to output the word economic. It's irrelevant to look at, say, the and these earlier words. So that's working well. And what's also very interesting is that we can see the capacity at work here. Because if you cast your mind back to the very first slide I talked about, this fixed context, that version of the same data structure would just be a 1D slice where you'd need to find all the right alphas that would be applicable for all the types of translations that you might want to do. And as you could kind of see, that's a very limiting scope of design for this model, right? And so now that we have this ability to have this sort of high capacity context vector, we can have a much richer set of representations where each word can in the generation of each word, we know which of the earlier elements to really lean on, to focus on in terms of the internal representation as we generate it. And so what else was extremely exciting to folks as they start to develop this type of mechanism was they saw much more complicated behavior that they knew was necessary to do very well-performed translation tasks. Because obviously even simple models could do this one-to-one correspondence, right? You could even just do a simple version of that with a lookup, but that's not going to be good enough for many types of translation. And so let me highlight another thing they saw happen, and that is at the time when they want to generate the word or the sequence of words, European Economic Area, what they saw the mechanism learn was that this is the French, right? And because of the way French is written, when they say this phrase, they start with zone first. So we see here, they say, l'accord sur la zone économique européenne, right? And then so now they want to translate this sucker. And so what do they see? They see the attention mechanism is most of the time, it knows that I can do this one-to-one correspondence, great, I'm done. But then learned that for me to translate the word area, I have to actually go, if it just naively had used, the next aligned word, it would be using the wrong word, European-y, right? And notice that it completely ignores that. So it's beautiful, right? It completely ignores that. It knows that for this particular word, it should go back and look at the word zone if it wants to, if that's the information it really needs to lean on, if it's going to succeed. And there's no way you could encode this if you had this sort of original old school context vector, which is, that's the Yeah, we're done. We can go now. No, anyway, so now we understand attention. I want to tell you how it's evolved in terms of its usage. It's now being used in this interesting architectures called transformers, and it's sort of changed shape quite dramatically. But we can still recognize these sort of underpinning ideas there. This is what attention looks in modern transformer architectures and variations of it. And then when you look at it, you might say to yourself, whoa, it's completely transformed. Whereas what's going on here? Well, the same function is still doing the same basic task that I talked to you about earlier. So if you look at it, it's still two nested functions being done. We have this internal role here that's essentially trying to calculate a weight, right? As I sort of unpack it, you're going to understand this better. But even though it now looks completely different, I want you to understand that everything I said to you up until this point still holds. It's still fundamentally just that, hey, let me figure out what's the appropriate weight between for the other inputs I'm trying to encode and what's the information I want to mix in there. And then it's just a normalization so that these weights across these other sources of information still play nice. So it still has a sort of weight-like semantic. That's all that's going on here. And then the interesting thing, it's super common in neural networks, is that the core motivation for this was, as a follow-up piece of thought, was we really like the mechanism, but it's too heavy. We want to make this thing, we want to have these architectures be ginormous and see what these suckers can do when we put lots of information and data trained through it, but the original mechanism is too heavy, so we can't scale this thing up. So let's think about a way that we can design some other types of equations that have a similar behavior, but yet are far simpler to compute, so therefore we can scale these guys up. That's the real motivation for changing, at least in my opinion. And so let's see a little bit more about how these things operate. This is a different view of what we've already seen in one of these modern architectures. And so let me just reorientate our view again, so we're not sort of lost. If I get lost, I stop listening to the person. So again, let me remind you what this particular type of diagram is saying in relation to the earlier ones. E's at the bottom are, you can think of these as raw pieces of information being encoded, or you can think of them being earlier, you could think of them being intermediate results somewhere in a deeper set of layers. But just for the sake of thinking about it, let's just think of them as words words that we want to eventually translate. And then think of this block that we're looking at as a zoomed in piece of a much bigger architecture. We want to have this neural architecture heavily use this idea of attention. And then so that, and we're focusing on just what we're going to do with respect to one of these words. And that word of focus is E2. So this sucker, this guy right here, E2, okay? And then we're going to apply this, this revised form of attention that's roughly doing the exact same thing to do two things. We're in this sort of fragment of this neural architecture, we're going to revise our representation of this word, or sort of hidden layer of this word as we're moving deeper. And we're also going to include the context vector implicitly, because when you look at this illustration here, you might sort of wonder to yourself, where is this context vector gone? I don't see it anymore. And this guy's telling me that it's still there. Well, the thing is the way that it manifests in new, more modern neural architectures is that it's just baked directly into the representation. And so we still have this equation here that's performing the attention mechanism, as well as updating the hidden state of this of these words as we progress through it. But they've lost the explicit representation of the context vector in this latest form. And so let me explain a little bit more also about what we see here. We are focusing in on this E2 word, and then there are a couple of things happening. One is you see this arrow going upwards. This is the representation of the word being propagated upwards to be also revised against these other operations. And these other operations here are performing the attention mechanism. Because we're looking at E2, if we just, this side view here is showing us just what E2 does with respect to E1. And what we see here is that we're doing two things. In this line here, we're updating our internal representation of E. And then on the left-hand side here, we have this thing called query key value. And so these, the way to understand this is that this query term, which we see appear here, the notion that the notion you should get is that we're going to query the adjacent EI word, the adjacent word. We're going to query it with respect to, we're going to query it based on updating the representation of E2, and we're going to see it, how much should the representation of E2 be revised by the value of E1. So that's what's going on here. We have the query, the value, which you see going straight up. So we have access to the direct value of the current representation of E1, but then we're going to modify it based on this weight that we learn. The weight that we learn as to how much E1 is going to matter to E2 in this representation. And so the reason why this style of encoding attention is so scalable is that all of these terms here, you might look at this and say, whoa, where are the learnable parameters? There's not many of them. And in fact, when you look into this type of architecture, the learnable parameters are much smaller than you might first think. They actually appear just here. So we have 3, in this case, in the case of comparing E2 to E1 for revising this internal representation, we only have to consider learnable parameters for these 3 matrices to get the same behavior that I talked about before. So it's really highly scalable type of neural architecture design. Once we have that fragment, what people do is just stack these guys on top of each other. And so when you look at larger transformer architectures, you often hear about this multi-head attention design. And so all that is having duplicate forms of attention being run in parallel. And essentially, there's a few other details here, but essentially just concatenating them together as you go upwards in the architecture. And so the reason why people have multiple forms of attention is that providing that type of capacity in the network allows it to learn distinct relationships independent of each other. So for example, you can have one attention that's specializing in one head of attention specializing in these sort of one-to-one mappings in a translation. The other one might be specializing in longer scale time, longer time encodings of what the subject matter is in the text that might modify what's an appropriate word to use. So you can have these all these different types of relationships being learned, and what's really nice is that they can all be executed in parallel. So there's no dependencies between these moving parts here. So again, you can scale them on top of each other. And what's also interesting is that by having this form of design, you can have attentions of attentions of attentions all stacked up. The other fascinating thing is that when you go back to the earlier design, the very original design, the use of this mechanism, if I just go backwards here, let's go back to the original design. The key innovation was the way that they generate the context vector, right? But then what you'll notice here, do you see this? Yeah. The way everything else is standard. So they're using all the types of recurrent architectures that Ferenc was telling us about on Tuesday, right? So for the encoding, it's just a regular bidirectional RNN. For the decoding, it happens to be a gated form of RNN. Remember, he was talking about GRUs with their gatings. So everything else except for the way that generates the context vector was standard. But now, as we move forward into this new sort of modern way of using these same ideas, what's happened is not only has the attention mechanism being not only has the context vector been kind of subsumed into the whole architecture, but we don't have any other type of architecture being used for doing encoding or decoding. It's all just attention. So as I show you in a couple of slides time, a full-sized, all of the architecture from start to finish, you'll see that there's no special architecture used for encoding. There's no special architecture used for the decoding. It's all just stacked attention, one after the other. that's been learned to do the same roles. And that's an interesting, that is why this follow-up paper that expand upon this original idea is called Attention is All You Need, because that's all the mechanism you need to build architectures of this kind. Let's see, I can probably go to, yeah, this is exactly what I want to get to. So on the right-hand side, we have a very conventional style of transformer. You can see inside it, or maybe I should use my cursor, you can see that it's using this multi-head attention. So that's the mechanism we've been studying. There's a few other parts to it that they're not critical, but they're very familiar to us already. So feed-forward networks are the very first ones that Ferenc was telling us about, these fully connected networks. And then we have some layers that are specializing in doing normalization and so on, but they're not the critical pieces. When we start to contrast the very first design, that was really a big enabler, right, in how it provided the generation of context. We can see that, yes, I was mentioning, the encoding is now being done completely by one of these very fast, lean, efficient forms of attention blocks, as that's what's shown in red. You'll see the yellow here that does the encoding, that sort of generation, in this case, the machine translation generation, trying to figure out what sequence of words are appropriate for the input, is now, again, also just an attention block. And then it's being stacked together to allow us to do some end-to-end training, whereby we have our input encoding here is wired in to another attention block here where we're encoding our outputs, and then it's stacked on top of this this other attention block again to produce our output. So you can see everything's being replaced with this recurring architectural design. Yeah, a few other points we're not diving into, but in terms of details that are important for how this works. If you're using these architectures on sequences where the order of the words or the order of the inputs matter, you need to do what's called positional encoding, which is essentially appending you can think of appending a sequence to these tokens that are coming in. So when they come through, for example, the attention, the ordering is maintained. And also, as I remember Ferenc was talking about just at the end of his lecture, it's very common to not put in just raw inputs. You'll see here it says input embedding and output embedding. That is a projection into some space that allows the inputs, the relationship between the inputs, for example, words, to be made more explicit to the model, so it more easily learns that. So for example, rather than just insert some encoding of certain words, you can normalize those words and then project them into a space where their position describes their sort of semantic relationship to other words, and it turns out that is a better way for the learning to occur. So I think this is the first time I showed some sort of results, but I've sort of hand waved about these methods are better. Early on with the original design of the mechanism, I was showing you how that there's the value in the type of attention in terms of one example, but here are some sort of quantitative results about why these methods, why this particular transformer version of these ideas were so exciting to people. And so you can see here at the bottom, these are two variations of transformers, and they're being compared to a variety of other methods for doing, I think this is machine translation. And then so machine translation has this particular way of assessing the quality called blue, where higher is better. And so what you can see here is that against other forms of approaches to doing this machine translation task, the transformer is much more is able to do this better than the other approaches. And then also importantly, because how I've been sort of emphasizing that by design, the mechanisms we're using here are scalable, you can see here that the training floating point operations are much lower. And so that, again, that's the, this necessarily isn't an apples with apples comparison here. The architectures at the bottom might be much larger capacity, but they're faster to train by the way that they're designed. So this was hugely exciting to folks. They can start to have machine translation, in this case, being done at a level they hadn't seen before, leaning on this mechanism. So that's the core. That's the core of the lecture. I'm now going to discuss a few extensions, and we can see what folks have been doing with these ideas of late. And then I also want to emphasize how the application space for these techniques are much richer than the NLP ones. Their foundations, their roots come from NLP. That's why I'm just talking about those terms, but they've been applied much more widely. So these designs are very scalable, but just like anything, there's always, let's see, how do I say this? There's always a certain part of it that becomes the bottleneck. So if you have lots of other nice properties that makes them very, very fast and so on, and you scale them up higher and higher and higher, there's this notion of Amdahl's law. I don't know if you've heard of it, but essentially whatever the bottleneck is will eventually come back to bite you, because you'll just make this thing super big, and then the slowest part will become eventually a bottleneck, even though it's not a dominant factor at the start. And so the dominant factor for transformers at scale is how they grow in complexity with respect to the length of the input, right? And the reason for that is that when you start building these things bigger and bigger and bigger, the attention blocks become really massive. And so because the attention considers the relationship between all of the inputs and all the outputs, and it grows with a squared complexity. So as you have like bigger and bigger inputs, that becomes a bottleneck to you building larger architectures. And so two places people have invested a lot of time is thinking about how do we overcome this bottleneck. And so two well-known approaches to this are known as reformer and linformer. The ideas are very simple. The idea of reformer is shown on this figure. And essentially it's saying, if we have, imagine that we have these figures on the right-hand side are capturing this notion of attention. And then if we have to maintain states to record all of these relationships, it gets too large, right? That's what I'm saying. So what you can do is you don't have to be completely faithful to recording all of these relationships. You can actually, in this paper, what they've done is used hashing. So they have a hash to record an approximate internal state of the relationship between one element to the next. So then they hash those values, and they also can do a second step, and that is cluster those values together, and then have those clusters only work locally within each other. So this is what's being shown down here. So rather than calculate the full attention from all inputs to all outputs, what you can do is just operate in a very local environment, and they find that even if they reduce the scale of attention to just the local neighborhoods, they can do this and still get most of the benefits of the architectural design. And this is a very similar story to what we saw last Thursday when I showed you different types of convolutions, and there was a variation called group convolution, whereby you don't consider the full possible range of connections, but you group the convolutions in distinct blocks, and they just operate locally between each other, and the relationships learned are still powerful enough to have most of the capacity of the original design. So this is one variation of transformer. Oh, I can give any. I'll give you a chocolate. I forgot to give you one. Yeah. Right. So this is a good. This figure lets us understand what's the power of the reformer. I think the most important thing to look at is on the right-hand side. We can see this bottleneck on the y-axis of sequence length, and then the original design of attention is plotted on the in the white. And so you can see that it's increasing as we get the increasing sequence length or batch sizes. So what's interesting is that the other colors are variations of reformer, and you can see that they are scaling very nicely. There's not much growth there, even as we increase the sequence length. Now, they do have a limiting factor, but here we have a pretty good behavior. Let me tell you about Linformer. This is another idea for simplifying this bottleneck in transformers that again has echoes of the designs of what we see happening in CNNs. The idea is that if you look at this this equation here, which is just the same description of attention that we saw earlier, what these folks do is they treat this calculation as P, and then they decompose P into a few smaller matrices. And so there's a bunch of linear algebra methods you can use to decompose a big matrix into smaller ones. But they approximate the original calculation just by breaking the big matrix into a series of small ones and seeing the values to be good value, seeing those matrices to be the right values, such that the output is pretty similar to the true behavior of the whole thing. And so when they do that, they find these type of results. So on the right-hand side here, again, we see the sequence length increasing. We see a conventional transformer having a very increasing in its complexity with respect to the batch size and sequence length. And then we see these variations of Linformer, which are very simple ideas, being much more flat in how they grow. And so to realize that idea of breaking down these large matrices into smaller ones, the actual change to the neural architecture is very small. So on the left-hand side, we see one view of the conventional way that you calculate this attention block. And then simply just by introducing two new matrices that are going to do a projection. So they design them so they're going to do a projection to a lower matrix. And then they actually have the architecture learn what that projection should be as a way to kind of realize it. Yeah, so, and yeah, good performance. The final variation of transformer that I want to mention is something called switch transformers. I won't sort of dive into the sort of the details of them, but that is to say that there is another type of bottleneck in the design of transformers, and as they grow very, very large, the bottleneck comes from these feed-forward components within the module design. And so and this can actually cause not only a bottleneck in terms of this growth in the input, but it can also be a bottleneck in terms of training time. And so these switch transformers, what they do is replace the complete original feed-forward network with a series of much smaller feed-forward networks that they then ensemble to create a very similar behavior. So it's a kind of a similar idea to the decomposition one, but essentially they have smaller versions of fully connected networks that they then switch between, and then and essentially, depending on the input, they'll have different mixtures of these smaller feed-forward networks acting in place of these much larger feed-forward networks. And so again, simple idea, but these are all kind of necessary ingredients to us to having much, much larger transformer models of the kinds that you've heard of probably in the news, like GPT-3 and so on. Because that sort of idea can actually have a giant increase in the training performance. And so that simple idea that I just described allows a 7-fold increase in training time, because we don't have to deal with updating all these parameters that fully connected networks have inherently built in. Yeah, blah, blah, blah. So let's close by considering a few different sort of applications of transformers. We've talked a lot about NLP. I'll mention that they can be used for images. I won't sort of go into this too much in detail because we're going to hear a lot about it next week. So next Thursday, there's a guest lecture on this particular topic. But I just want to say, one of the considerations you sort of are faced with when you want to use this style of architecture on a task like a visual perceptual task is that you have to figure out how am I going to munge or produce the input to the encoder, right? So there's not really like an obvious natural mapping of an image such that you can kind of capture all its interesting sort of semantics and so on. And so that it can be easily consumed by a transformer. So the original paper that started this sort of exploration of vision tasks as they applied a transformer did something quite straightforward. all they did was, and this is after they found that sort of obvious things to do, like linearize all the pixels out just sort of one after the other, were not being effective. What they realized that it was effective was simply to break the image into a series of patches and then come up with a special type of projection for those patches that is based on similarity. So essentially, so it's very, very similar to the idea of words. You have this projection rather than give it the raw patch. You actually use a projection of the patch from the image into some space where the similarity of patches are maintained. And then that is what you give to the transformer. They did that and they found that they were getting excellent, excellent results. And we're going to hear about this next Thursday. When they do this and then they visualize the type of attention that is learnt, they do find that it sort of behaves the way that you would hope the machine is sort of behaving. And so in an object recognition task, you would hope the attention is learning that certain parts of the image that are informative for doing the classification would be what a human would also think would be important, right? Would be alarmed if the way that the machine decides to recognize dog was predominantly based on seeing grass around it, right? That would indicate to us that there's something sort of generate about how it's being trained or what it's actually learning. But what they found is that when they visualize the attention, so this is kind of just a different way of visualizing the attention, so you can kind of see what parts of the image the model is really focusing on as it makes certain decisions, roughly corresponds to what you hope is happening. Dog, there's a lot of attention being associated with the dog to recognize the dog, and the same with plane and so on. Let me go a bit. Yeah, there's a story there. Yeah, I think there's, I'm not sure what the counterexample is there, but that's right. The snake is not really being looked at, and I guess yeah, it's true.
The snake is trying to camouflage itself, right? Like it's probably colored to camouflage the rocks.
That is true. Yeah, so, yeah. So I guess maybe the snake is like an adversarial example.
This is why the robot will be killed by poisonous snakes if they develop it.
Yeah. Let me go through this a bit more. Yeah, so but it's essentially people are very excited about transformers because they find as they go to different tasks, there's a single approach to an architecture is outperforming the other variations of architectures that we know to normally do very well on certain tasks, like CNNs have always been very popular for visual tasks. And now we find that transformers, the machinery they provide to us, are able to exceed that of CNNs. But I have a comment on that at the very end of this talk. Yeah, let me get to this is another example. One thing that might be interesting to you is that some of these other types of machine learning tasks that would be in the news, such as using machine learning to do things like protein folding prediction and so on. If you look at the architectures that are inside the machinery that are being used, and for example, just this case of AlphaFold as an example, we can see that they're using architectures we've been discussing in class. So the very first version of AlphaFold, of course, there's a lot of things going on, lots of moving parts to produce this type of predictions. But the neural architecture component of this particular application in the very first version was using CNNs that we looked at 1 week ago. By the way, the way to interpret this y-axis is that 90, this is doing prediction of experimental outcomes, and you hope the machine is able to do as well as actually doing the experiment yourself. And apparently a score of 90 or above means that the machine is predicting at a level that is the same as, or perhaps better than actually doing physically the experiment. And so getting to 90 is a very important benchmark to hit. The reason I'm mentioning it is that 2018, they're using CNN architectures that we're seeing. 2020, the 2020 result is using a transformer. So again, we see the diversity of the applications of this style of learning sort of proliferating and doing very well. So that's what I want to say about transformers. I think kind of it provides us with a sort of good solid grounding about what you should know, what the basics are, why they succeed, where they came from, and now what they're being applied to. One final thing I thought we could maybe, if we have time to discuss a little bit, is a very recent result. So when we first started doing this course last year, the message we gave about transformers was very exciting. And if you had to bet, you might suggest that transformers end up replacing every other architecture we currently know. And then so folks have been digging into seeing if this is really the case. And one interesting result that came up very recently was that it's sort of similar to one of the results that friends were showing us earlier. What they did was that in parallel to coming up with neural architectures, people are always coming up with a variety of sort of heuristics and tricks that they apply to the training process. They throw it into the mix and they see the architectures going better and better and better. And so what folks have done is looked at the whole body of tricks that people have come up with for training models better, and then applied them to convolutional networks and systematically saw if I compare a transformer and I start to use or remove these series of tricks, how do transformers compare to just regular convolutions? And the takeaway is that they start to see a regular convolution with all the different ideas that we have available to us now, it starts to perform just as well as a transformer. And so that starts to sort of, it definitely suggests to us that the jury is still out about, you know, are these architectures going to dominate? What is really appropriate, and what's actually really shifting the needle in terms of performance? And so it's a very experimental type of science, so it's kind of hard to sort of separate concerns. So these types of experiments are really critical. But with that, I'm happy to take questions.